Let's start taking a look at AC circuits. I want to spend some time on this because not only is it the basis for our power distribution system, but it also helps some other things such as radio. In order to understand an AC circuit, we have to recognize that the A stands for alternating. And you can see on the screen a graph of current as a function of time, and the plot is sinusoidal, oscillating up and down from a positive maximum to a negative maximum. This same sort of curve also applies to a voltage. A voltage in an AC circuit also oscillates up and down sinusoidally, and it does so at exactly the same rate of oscillation as the current does. The maximum value, whether it's the current or the voltage, is called the amplitude and is typically represented by a capital A as a general symbol. In the case of AC circuits, the quantity period, denoted by a capital T, is also something of importance. It has units of seconds, but sometimes it's nice to think of it as units of seconds per oscillation. As you can see on the screen, with the horizontal axis representing time, the period capital T represents the time that must elapse to go from one peak to the next peak in the oscillations of the variable in question. We also have another quantity that we're going to have to worry about, and that is called the phase shift. Not all sine waves have to start exactly at the origin, like sine x starts at the origin, but we're going to find that sometimes there is a deviation in where the quantity is in its oscillations when it starts. And the quantity that allows us to accommodate that is the phase shift. So get used to that. We're going to be taking a close look at it as we go through the different circuit elements that can be found in an AC circuit. A typical equation would be that the voltage as a function of time is equal to the amplitude times the sine of omega t plus phi. A is the amplitude. It is the maximum voltage in this circumstance. And of course, in the case of current, as we saw, it would represent the maximum current. Omega is the angular frequency. The angular frequency has units of radians per second. It is related to the frequency, and that's a rather annoying idea. There is angular frequency and there is frequency, and they are separate quantities. Frequency is what you typically think of. It's how many times per second something happens. The frequency is equal to 1 over the period. The angular frequency is kind of a conversion factor. One oscillation is similar to one full rotation in circular motion. And in circular motion, we worry about angular velocity, which is represented by the lowercase Greek letter omega, and has units of radians per second. Well, omega is going to serve as a conversion factor. It's going to take this measurement in time and convert it into radians so that we can use it as the argument in our sine function. Of course, we also see plus phi, where phi represents the phase shift. One of the interesting characteristics of the sine function is that its average value is 0. And that can lead to a little bit of an issue. If I wanted to quantify the average value of the current or the average value of the voltage, it is technically 0. But that doesn't give much information because it could be 0 with a maximum oscillation of 1 volt, and it could be 0 with a maximum oscillation of 1,000,000 volts. And there's another quantity that is often used to convey the amount of voltage or the amount of current that is actually involved in the oscillations. And this is called the root mean square. The root mean square is a pretty literal expression, except instead of going left to right like you would in a regular sentence, we have to read that from right to left. If we take a sine function and we square it, we are always going to get a quantity that is non-negative. It's always going to be greater than or equal to 0. But it turns out that the square of a sine function is also itself a sinusoidal oscillating function. Since it is now no longer less than 0, if we were to take the mean of the square, we would get, as it turns out, 1/2 the square of the amplitude of the original function. And then we take the square root of that result to get back to the original units. So when we talk about root mean square, we're talking about the square root of the mean of the square of the function. So it's a rather awkward approach, but it gives more useful information than the actual average value of a sine function, which is 0. The relationship between a root mean square value and a maximum value is square root of 2. The root mean square of whatever equals the maximum value of whatever divided by the square root of 2. And in most colloquial issues, most everyday language issues, if you talk about a voltage from a household outlet, you're talking about the root mean square voltage. We think of our household outlets as providing 120 volts. That's the root mean square value. It's not the maximum value. The actual maximum value would be 120 times the square root of 2, which means that the maximum voltage we get is actually 169.7 volts. So when we have an AC voltage source and we use one of our electrical outlets, it's actually a voltage that is sinusoidally oscillating from positive 169.7 volts all the way to negative 169.7 volts and back again. Now, I want to point out that the angular frequency when we look at a current and when we look at a voltage will be the same. And if we stick to standard values, U.S. electrical standards, the frequency is 60 hertz and omega is equal to 2 pi times f. 2 pi times 60 is about 377 radians per second. So that will be a typical value, and that angular frequency, as I said, applies to the oscillating current, and it applies to the oscillating voltage. Of course, the amplitudes of the functions that we use to describe the current and the voltage will be different because current is not voltage. But there's also going to be an issue with the phase shifts. That's going to depend upon the different circuit elements that exist in a circuit. But if I have this driving, oscillating voltage source, the current in the circuit might not be in sync with the voltage supplied by the source. And that's one of the things we're going to be exploring. We're going to be taking a look at the phase shifts for voltages across a resistor, across a capacitor, and across an inductor compared to the current through the circuit. And the current through the circuit is kind of our reference because the current in the circuit is provided by the driving voltage. And the current through the circuit at all times, if we're looking at a series circuit, is the same, whether we have a resistor, an inductor, a capacitor in series. Whatever's in series, the current through each is the same at any given instant in time. But if I have a resistor and an inductor and a capacitor all in series with each other, it's certainly not at all the case that the voltage drop across each of them will be equal to each other. Let's start by looking at just a resistor hooked up to an alternating voltage source. And you can see the circuit diagram there and the representation for this alternating voltage source with kind of a sine wave in a circle. and a capital V to represent the fact that this is a voltage source. This is the friendly one. This is the nice one. We'll be looking at an inductor and a capacitor. Those won't be so nice. Resistors are nice. Resistors are nice because of Ohm's law. Ohm's law says that the voltage difference across a resistor is equal to the current through the resistor times the resistance. Now, the resistance is a device-dependent quantity. It doesn't depend upon the current in the circuit. Well, as long as it's an ohmic material, and that's all we're looking at. So, at all times, the voltage across the resistor is going to be equal to the current through the resistor times the resistance. So, the voltage and the current will always be in sync with each other. The voltage across the resistor will always be in sync with the current through the resistor. Mathematically, we would say that the phase shift for the voltage across the resistor is 0. It's not as nice for a capacitor. The phase shift is not going to be 0. What is the phase shift going to be? Let's consider an uncharged capacitor hooked up to a sinusoidal voltage source. The current is not going to be in sync with the voltage across the capacitor. Why is that? Remember that the capacitor is starting off with 0 charge on it, which means that the current that initially escapes the voltage source doesn't see anything trying to slow it down. Once current starts building up on a plate on the capacitor, that charge building up on the plate is going to slow additional current, trying to add yet more charge to the plate. So as charge builds up on the capacitor, there's going to be a decrease in the current in the circuit. So charge goes up. You might recall that for capacitors, that Q equals C times the voltage across the capacitor. Q equals CV. So if Q goes up, V goes up. So there's going to be that asynchronicity because as the voltage across the capacitor is going up, for instance, the current through the circuit must be going down. So they are not going to be in sync with each other. Exactly how will they not be in sync with each other? We'll take a look at the pair of graphs superimposed on each other on the screen. We'll start off with our current represented in blue. You'll see that it starts off at a maximum. It's like it's obeying a cosine function. Whereas the voltage across the capacitor seems to be obeying a sine function. Now, why is that? The current is maximum when the charge on the capacitor is 0. Remember, once we start building up charge on the capacitor, that's going to act to slow current down. So when the current's maximum, the charge on the capacitor is 0. When the charge on the capacitor is maximum, the current in the circuit is 0. All of the charge in the circuit has been placed on the plates of the capacitor, at least for a split second. And because there's no charge moving in the circuit, the current in the circuit is 0. So what we have is when the current in the circuit is maximum, the charge on the capacitor is 0, and that means that the voltage on the capacitor is 0. On the other hand, when the current in the circuit is 0, that means that the voltage across the capacitor is maximum because the charge on the capacitor is maximum. And if we follow this driven sinusoidal behavior, remember this external voltage source is driving this behavior. If we follow this behavior, we get the repetitive behavior that we see on the screen for these two quantities. If we take a look at the difference between the sinusoidal current and the sinusoidal voltage across the capacitor, we see that the current reaches a peak, and then a moment later, the voltage across the capacitor reaches a peak. And that moment in between the first reaching a peak and the second reaching a peak amounts to a quarter of a full cycle. If you go back to the previous graph, you'll see that the current is at a peak when the voltage is at 0. Then a quarter of a cycle later, the current is at 0 and the voltage is at a peak. So the voltage's peak is about 1/4 of a cycle behind the peak of the current. And so we can say that 1/4 of a cycle, if a cycle is 2 pi radians, 1/4 of a cycle is pi over 2 radians. The current is leading the voltage across the capacitor. And so the phase shift for the voltage across the capacitor is minus pi over 2 radians. Remember I said earlier, our current is going to be our reference. We want to measure the phase shifts of the different circuit elements with respect to the current. So the voltage across the capacitor is going to have a phase shift of minus pi over 2 radians. And we are going to express our current as having no phase shift. Our equations in that context, the voltage across the capacitor as a function of time is equal to the maximum voltage times the sine of omega t minus pi over 2, while the current as a function of time is simply equal to the maximum current times the sine of omega t. Now, is there a relationship between the maximum current and the maximum voltage? Certainly in the case of when we were looking at a resistor, we will use Ohm's law. Is there something similar to Ohm's law? Well, since I'm raising the question, you can probably figure that the answer is yes. But not only do we need the maximum voltage, we also need the capacitance, capital C, and the angular frequency, omega. Now, what is going to be this relationship that allows us to figure out what happens with the maximum current based on these other quantities? Now, it shouldn't be a surprise that the larger the maximum voltage, the larger we can expect the current to be. That isn't really any different than what we should think of from Ohm's law. But it's not a resistor that's involved here. It's a capacitor. Now, the charges on the capacitor act to slow down the current, just as a resistor can act to slow down the current, but there is going to be a little bit of a difference. What happens if capital C, the capacitance, gets larger? How can you visualize that? Well, recall that capital C, the capacitance, is equal to epsilon naught times capital A divided by D, kappa times epsilon naught times capital A over D if you have a dielectric material. The capacitance goes up as the area of a plate goes up. Now, imagine that we increase the capacitance by increasing the area of each plate. What that means is that as charges are dumped onto the plate, they are dispersed over a larger area rather than being concentrated into a small area. So the more they are dispersed over the larger area, the less their ability to slow down additional incoming current. So the larger the capacitance, the greater the maximum current can be. We also have omega. And omega is going to be a measure of how fast the actual current is moving. Because the greater the angular frequency, the faster these charges have to get onto the plate and then be removed from the plate. They have to be moving at a pretty good clip if omega is very large. So a larger omega tends to lead to a larger current in this capacitor circuit. If we combine these observations together, we get this expression that the maximum current is equal to omega times C times Vmax. But what we do instead is we try and mimic Ohm's law. Ohm's law says that the current goes as voltage divided by something. If I take my original expression of omega times C times Vmax, I can rewrite it as Vmax divided by 1 over omega c. Algebraically, that's perfectly acceptable. And this quantity 1 over omega c is rewritten as a capital X subscript c. It acts a little bit like a resistance. And what we have is something that kind of mimics Ohm's law. The maximum current is equal to the maximum voltage divided by X subscript C. X subscript C has units of ohms, but it is not resistance. It is not technically a resistance. It is called the capacitive reactance. And bear in mind, this only allows us to predict the maximum current compared to the maximum voltage. It does not apply at every instant in time. It only just says I can predict the amplitude of the current based on the amplitude of the voltage, and that's that. Take a look at this conceptual question. We have a parallel circuit in which our alternating voltage source is hooked up to a capacitor along one path and a resistor along the other path. And the question is, what can we say about the voltage difference across the capacitor compared to the voltage difference across the resistor when they're in parallel? Are the voltage differences equal at all times? Does the voltage difference across the capacitor lead the voltage difference across the resistor? How about the voltage difference across the capacitor lags behind the voltage across the resistor? One of those three. Let's move on to our final circuit element, an inductor. And this is probably going to be the most challenging to visualize because Lenz's law can be so darn difficult to visualize. The fact that we have a coil in this circuit means that there is going to be a substantial magnetic field created by this alternating voltage source. And this substantial magnetic field is going to be changing in time. And because this substantial magnetic field is changing in time in a coil, there's going to be back EMF generated in the coil. That back EMF we're going to call V subscript L, the voltage across the inductor. And if you'll recall from a recent lecture, the voltage across the inductor is equal to minus capital L, which is the inductance, times the change in current over time. In other words, the more rapidly the current is changing, the greater the back EMF in the coil, in the inductor. Now, when is this current changing? When the current is at a maximum, it's actually not changing very much. It's when the current is close to zero that it's actually rapidly changing. It's, for instance, changing from a positive quantity to a negative quantity, which is a pretty big change when you think about it. So when the current is close to zero, it's changing most rapidly, and that's when the voltage across the inductor is at its greatest. So how does this work? If I have the voltage across the inductor at zero, when the current is at a maximum value, whether it's a positive maximum or a negative maximum, and if the voltage is at a maximum value when the current is at zero, we can get an overlay of the two graphs as it appears on the screen. And the voltage across the inductor is trying to regulate the current in the circuit. The inductor is always trying to bring the current back to equilibrium. It's trying to pull the current back to equilibrium. And so it's leading the current. It's like the current has some momentum, and the voltage across the inductor is trying to pull it back in the opposite direction. So the voltage across the inductor actually occurs at a maximum, actually occurs before the maximum in the current. So we can say that the voltage across the inductor leads the current through the circuit, or the current in the circuit lags behind the voltage across the inductor. Once again, just like with the capacitor, the magnitude of the difference between the occurrence of the peak in the voltage across the inductor and the occurrence of the peak in the current is 1 and that is pi over 2 radians. But now, because the voltage across the inductor leads the current through the circuit, the phase shift for the inductor is positive pi over 2 radians. And our expressions for the voltage across the inductor compared to the current through the circuit. The voltage across the inductor is equal to the maximum voltage times the sine of omega t plus pi over 2. And the current we're still leaving as our reference, meaning we're going to keep its phase shift at 0. So I max times the sine of omega t. With our equations in hand, again, we're probably going to ask, is it possible to come up with a relationship between Vmax in an inductor and Imax for the current? And of course, the answer is yes. And probably not surprising, we have to consider the inductance, capital L, along with the angular frequency, omega. But what is the relationship between these three? Again, the larger the maximum voltage, the larger you should expect the maximum current to be. Nothing new there. But remember that the inductance is a measure of the ability of the device to provide back voltage, back EMF. The larger the value of L, the greater that back EMF, and the more effective it is at slowing down the current. So a larger value of L leads to a smaller maximum current. In addition, the inductor behaves differently than a capacitor or resistor because the inductor depends upon how rapidly the current is changing. And if omega is large, if the angular frequency is large, that means that current is rapidly changing. And the more rapid the current changes, the greater the back EMF. So if omega goes up, the back EMF goes up, and the maximum current will go down. If we combine these observations, we get that the maximum current is equal to the maximum voltage divided by omega times L. That quantity, omega times L, is equal to capital X subscript L, which is called the inductive reactance. And it acts similarly to the capacitive reactance and slightly similarly to resistance. But once again, like with capacitive reactance, it only allows us to determine the amplitude of the current compared to the amplitude of the voltage. It is not going to tell us the current at all times if we know the voltage at all times. Let's take a look at this conceptual question. We have an alternating voltage source represented on the left, and then we have a parallel circuit. One path of this parallel circuit has an inductor. The other path of this parallel circuit has a light bulb that acts like a resistor and a capacitor. And we want the light bulb to glow most brightly. Which situation will lead to this light bulb glowing brightly? Is it going to be when the voltage source oscillates at very low frequencies, when it oscillates at very high frequencies, or at a very particular value where the angular frequency is equal to 1 over the square root of L times C? If you have questions, ask them in class. Take care. Bye-bye.